Hi! In this video, I'm going to explain what the human-machine interface is, why it's important, and of course, the neuroscience behind this technology. The human-machine interface is a system that allows signals from the brain to control external devices such as prosthetic limbs or motorized wheelchairs. It provides a new and direct pathway of communication between brain signals and external objects without using the normal neuromuscular output channels. This technology identifies brain signals, analyzes them, and translates the neural activity into output commands to carry out the desired action, such as moving a robotic arm. The purpose of this interface is to restore, replace, or improve functions for people who are disabled by neuromuscular disorders or those suffering from spinal cord damage and paralysis, as well as improving the quality of life and reducing the cost of intensive care. This advancement in technology is considerably important since globally, the burden of neuromuscular disorders is continuing to increase. As populations are growing and aging, so is the prevalence of neuromuscular disorders such as cerebral palsy, lateral sclerosis, spinal cord injuries, as well as people suffering from locked-in syndrome, where they have no means to communicate other than eye movement. Neurological disorders continue to be the leading cause of disability and are the second leading cause of mortality worldwide, causing 9.4 million deaths in 2015 alone. It is clear that an increase in demand for treatment, rehabilitation, and support services for neurological disorders is only going to continue to grow. Human-machine interfaces are able to assist in improving the quality of life for people who are disabled by neuromuscular disorders that lead to the loss of voluntary motor control and the subsequent loss of communication, as this technology intends to facilitate motor skills and communication for people with physical impairments, as well as progress neuronal rehabilitation for those who have had a spinal cord injury or a stroke. This is possible as it is a system of neurotechnological devices which detect and measure brain activity generated from control signals. Here, we will be focusing on the application of electroencephalography or EEGs in human-machine interfaces, as it is the most common, non-invasive form of neural recordings, where the brain signals are converted into a computer-generated output, which then carries out the intended task. This creates a new, non-muscular channel for relaying a person's intentions to external devices such as controlling a prosthesis, steering a wheelchair, or utilizing speech synthesizers. In principle, any type of brain signal can be used to control a human-machine interface system. However, we will be looking specifically at a category of human-machine interfaces that are built on the rhythmic activity recorded over the sensory motor cortex, where the sensory motor rhythms are used to command a specific output. These signals are measured by scalp EEGs, where electrodes are placed on the surface of the skull. In this case, focusing on the precentral gyrus on the central sulcus to record the microvolt level extracellular potentials generated in the cortical layers. In relation to sensory motor rhythms, these electrical signals are activated when the user performs a mental task such as motor imagery, where they imagine moving a specific body part such as closing a fist. These signals are recorded and translated to a specific output command. In order to appreciate the significance of this technology, we are going to compare a simple action between a traditional output pathway and the human-machine interface interaction. In the simplest terms, to get a cup of coffee, normally, information from the visual cortex is relayed to the cortical motor region, sending out signals to move the right arm. The signal is then carried by nerve fibers through the spinal cord to neuromuscular junctions. The signal is then transmitted across this junction by the acetylcholine neurotransmitter, triggering the arm to pick up the cup. However, this is not possible for people who have neuromuscular disorders, so the human-machine interface system acts as a new pathway that recognizes certain features of brain signals to indicate the user's intentions and then carries out the action, consisting of 5 sequential stages to achieve this, which are brain activity measurement, pre-processing, feature extraction, classification, and device output. In the brain activity acquisition phase, the brain activity of the user is captured through various types of EEG sensors. Then the raw EEG data needs to be amplified to suitable levels for electronic processing. Noise reduction and artifact filtering may also be performed to remove electrical noise or other undesirable characteristics. Feature extraction is the process of describing the signals by a few relevant values called features. These extracted features are then classified through different machine learning and deep learning algorithms in the classification stage to convert these features into appropriate commands for the device output phase, signaling the robotic arm to then pick up the cup. The acceptance of human-machine interfaces over the last 2 decades have allowed for significant developments to be made in this field. Future improvements are still continuously being studied to aim for an effortless prosthetic control, as well as developing electrode devices that are minimally invasive and more user-friendly. Additionally, Neuralink by Elon Musk is a human-machine interface initiative that is currently developing a system that will allow paralyzed individuals to use computers as a means of communication through just their thoughts alone. Human-machine interfaces provide hope for those who are suffering from motor disabilities, as it allows a person to communicate with or control external devices without using the traditional neuromuscular pathways. However, there is still so much research that needs to be conducted in this field to not only improve the technology and its applications, but to also understand the future social impacts, as well as establishing the knowledge and tools required for ethical and legal evaluation. Thank you.